how excited the molecules are. And root mean square. It just means what's the average speed of the molecules moving. And that's, so RMS means root mean square, which is a mathematical definition. And what we're really looking at is at a certain temperature, all the molecules are moving at a certain speed. And then based on their molar mass, they either move faster or slower, right? So we want to know what they move at a certain temperature, right? 3 RT. So here's the temperature. That's the variable temperature. And then this is molar mass of the gas, right? So pretty simple. This is going to be an easy one. So the question I'm going to ask on the test is very similar to this. It'll probably be a different molecule, so you'll have to figure out a different molar mass. But the one I talked about was find the mu for ammonia at 25 degrees C. Now, so it's a gas law problem. So Kelvin, atmospheres, liters, liter atmospheres, moles, right? That's what we usually want to be in. But here we're going to be molar mass, right? So we're good. So R in this case is going to be, what, 8.314, because we're in energy, 8.3, did I say 8.3? I said 8.314, and then I wrote 8.1. 8.314, what is that, joules, moles K, is that what that is? Joules, yeah, moles K. Okay, so that's R, and then let's just put it in the, oh, T is gonna be, right, T is gonna be 25 degrees C plus 273.15 K equals 298.15 K. And then the molar mass is going to be, right, N is 14. 14.01 or just 14? What does your table say?
Nitrogen is 14.007.
So that'd be 0.1.
Yeah.
Okay. Grams, and then hydrogen. We could do that. Let's just do that because it's 0.007 grams, and then hydrogen is 1.008 and times 3, right? So that's 2431. So 17.031 grams per mole NH3. All right. So we have everything we need to get the average velocity of the molecule, and it's really the speed. It's not really the velocity because it doesn't have a direction. That's okay. It's called. We'll just leave it what it is, what they call it. So 3 times 8.314 joules, moles, K. And Jules, do you think I'm talking to you every time I say that?
When you say kilojoules, it really upsets me.
That's good. Good one. And then 298.15 K. And then what are we dividing by? Oh, molar mass, 17.031 grams per mole. All right, and that's all under our square root sign. So this is the square root sign. The way I like to do these is I like to put this all in brackets and then do a bracket for the top and then divide by the bottom. So when we look at the units, right, this is where I get lost, right? Because the answer, let me put the answer up, and then we'll have to do the cute little trick that I forgot when I looked at it, and I'm like, I don't understand how I got there. 382 meters per second. And I'm like, what? Well, here my moles cancel. That's good, because remember this moles comes on top, so because it's on the bottom and then divided, so it comes out on top, so moles cancel. K's down below, so it cancels. And I'm left with joules. Oh, I did a boo-boo. I did a big boo-boo. Big, big boo-boo. This is in kilograms per mole. So I have to divide this by 1,000 times 1,000 grams, 1 kilogram. And so this becomes 0.01231731 grams. And then that becomes 0.017031 kilograms, but not kilojoules, because we don't want to upset her. And then, so now we're left in K's cancel, moles cancel, there. We have joules. The units are joules per kilogram. Wow, come on. There we go. But I'm in meters per second. Uh-oh. Well, and I'm looking at it, I'm like, okay, there's a kilogram there, so that's got to cancel out. Turns out, joules equal kilogram meters squared seconds squared. Kilogram meters squared per second squared. Yeah. And now, so if we take the square root, right? So we have joules here, but if we write joules, kilogram meters squared per second squared, right? Now, kilograms cancel, and we're in meters squared per second squared, and we take the square root of meters squared per second squared, and we get meters per second. Yay. So that's our speed. So that's how fast an ammonia molecule, a gaseous ammonia molecule, the average one, right? So if you have moles of gas, you have 6.022 times 10 to the 23rd molecules of ammonia floating around at the speed at 382 meters per second. That's pretty fast, right? If you ran 382 meters per second, you'd be the fastest human alive, right?
Yeah.
Yes, say yes, yeah.
Yes.
Because what, 100 meters, we can't even do that in 10, well, the fastest can now do it in under 10 seconds. That's pretty amazing. Like I can't even do 3 meters in 10 seconds. No, I mean, I can probably do it in 10. Yeah, time, yeah. But 382 meters, I mean, that's a football field, right? Almost. A little bit more. Right? Anyway, that's pretty fast. So a gas molecule can move from me to a football field in less than a second, right? So try to catch that if it has the ball. So that's why we're looking at that, just to give you an idea of what's happening and how fast gas disperses, which is why anytime you have a little bit of gas in one corner of a room, it doesn't take very long for it to get to the other. And remember, the bigger the molecule, the bigger the gas molecule, right? This is 17 grams per mole or 0.017, but the bigger the molecule, the slower it moves, but it's still moving very, very fast in comparison until you had like a gas. If you turn hemoglobin into a gas, right, it would move a little bit slower because it's a much bigger molecule. There are molecules that are, 1 million units, so that would move much slower. Imagine a gas you could see. That would be moving much slower. All right, so that was the one I wanted you to get out of that slideshow. Couldn't sign in. Any question on that? I mean, I think that's that's a gimme, right? The equation, if you can't remember the equation, it'll be on the equation sheet. So this is just a plug and chug. You have to recognize what it means, because I'm not gonna give you this part on, I'm just gonna say find mu RMS. And you go, well, I don't remember that one. And then, but look on the worksheet and see if you can assign something to it, would be the, I mean, you guys are all really smart anyway. You can probably do it without that. But like, when I take a test, I kind of lose my mind. So sometimes the easiest things become the hardest things. So really, now's your chance. Brittany's not here, you guys can ask questions. Yeah. All right. It's not gonna, see, that's why I love having her here, because if she's not here or someone's not interrupting me, I just start picking up speed, and then I just go without stopping. And then even though I know there are questions, I can't do anything unless you ask the questions. So I assume everyone's gonna get this correct on the exam, and they understand that it's motion. So if I just said, find the average speed of a molecule of xenon gas, you guys would just tear it up right now, right?
No.
No. Okay, so the 8.314 is a constant that we should know, right?
It will be on the sheet. You should recognize it,
Okay.
right? Because the other one you use, the 0.821 liter atmospheres moles K,
What's
is
the
for a different
three?
type of problem.
I see 3 times that. Where's that 3 come from?
From the problem he's standing right next to.
3RT. I'm blind. Okay.
All right.
I have a question.
Yeah.
Are we gonna go over any of the ones that has the two, gases? Are we gonna have any of those?
The partial pressures?
Is U of A over U of B?
No.
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 Okay.
No. That won't make the cut. It's too much. We're covering too many things in too short a period of time. So, no, the diffusion,
Okay.
we're good on that. Try to get to the slideshow, but it's not being very cooperative.
Will there be any definitions that we need to?
Yeah, there'll be definitions. There'll be definitions, probably coming directly from the reading quizzes.
Can you go over the bottom joules equals kilojoules?
Right. So.
Yeah, I'm not quite understanding how to take.
Okay, so-
the number we got plugged into that.
So the joules, right, is an energy number,
Yes.
but the definition is in this units, kilogram meter squared per second squared. And I can write this out, meters per second squared. Let's do seconds too. All right. So kilogram meters per second squared. So if we were doing this problem, we could write this instead of joules, we could write kilogram meter squared per second squared times 298.15 K, right? And we're gonna put our big, and then all over 0.017031 kilogram per mole. And what did I leave out here? Oh, this is still moles K. All right. So now when we go to solve the problem, K's cancel, right? Moles cancel because the mole flips up top. Then we have kilograms cancel, and we're left with the square root of meters squared per second squared. Yeah.
You're not taking the square root of the whole equation though, right?
Yeah.
Wouldn't the meter squared second, oh, okay.
Yeah, the meters squared second squared becomes meters per second.
Okay.
That tied in a little bit better.
Yeah.
Okay, now it's not here. Are you kidding me?
So just plug in everything in, multiply it out.
Yeah, but I'm trying to
divide it.
punch it on the calculator and I'm not quite.
Well, so again, what I like to do when I punch it in the calculator is I like to
Do that.
the whole thing, the whole bracket, then a bracket within there, and then do 3 times 8.1314 times 298.15 end bracket, and then divide by bracket, bracket, end bracket. And then take the square root after you do. I know I put those on here. How many slides? I only have 10 slides. No, this time. Wow. Okay. Oh, so 21 slides. Yeah, we're not doing. We're stopping right here. Oh, you guys can't see that.
We're blind.
Yeah, no effusion rates, even though it's, I mean, that'd be better. But we're gonna do the diffusion. So our one problem that we're doing with this is, oh, that breaks my heart. Okay. That's really bad. So I'm giving you guys a real break today, a real break all day. It could be, I could have got the wrong number, I don't know. That's why you should always check my work.
Can you follow yours on your calculator to see if that?
Oh yeah, I better try it, right?
Yeah. Because we're smaller than it.
Well, I mean, if you two got the same number, then I'll just change it.
But I don't know if we're taking into account that J equals.
But that doesn't change anything,
No,
so
it doesn't.
it's just the units.
It's just units.
So 3 times 8.314 times 298.15 equals divided by 0.01703 equals, and then square root, right? $660.
Yeah. Okay.
All right. So even faster.
That explains our confusion.
661 to be real. Is it 3? Is it 3? No.
No.
It's 2. So 660.
Well, yeah. I guess 25 Celsius would be our C.
Yeah. Without the decimal.
We wouldn't take our Kelvin conversion as our sig.
No, because no.
Okay.
So is it correct, or you need to change
It is now. It's
Answer
660.
660.
It wasn't 382. I don't know where I got 382 from, but it's not correct. And yeah, so
We now understand it.
moving to further action in the fourth quarter, Notre Dame is down by 7. When I was growing up, the only game you got on the weekend was Notre Dame football, and it came highlighted, edited. And so if they thought it was boring and they had to fit it into the time slot, that's what they'd say. Moving to further action, Notre Dame has the ball on the 12 and fourth quarter.
They just skip a bunch.
They just skip a bunch of plays. I mean, those were the days. 3 channels.
Yeah.
Now you see every football
Oh,
game all over
God.
the United States and even in England.
And they gamble on it.
Yeah, and you can gamble on it live and changing odds during the game. Used to be you had to wait till Monday to find out.
Another day at the races.
It's on. It's on. Okay. So this is the slide we were going to look at. Let's see, here we go. Right. This is the last slide of no, not new slide. Okay. So basically, what this says is that if you have a bunch of gas and the molecules are moving around, right? The rate of diffusion, that's the speed of the molecules moving, or how fast they travel to the outside edges, right? So that's what we just did. The average speed of a molecule in any container, which would be, this room would be a container, right? The average speed of an ammonia molecule would be 680 meters per second, which is fast, even faster, twice as fast as I said originally. And I don't know how I got half that. I must have forgot to multiply by something or something. Okay, so that's all we're doing for gases. And then what do I do? Just switch
And
here.
remember
Yes. There we go. Now I can, and then when we go back to, we need to probably review all the, what are those called? The quantum numbers, because that's where we were. That's the switch we made, right? Quantum numbers. And then the quantum numbers define the shape and the location. And it's based on the wave number. We call it the wave solution of a wave, and that describes the movement of a particle, and that's how we can decide where it is in space. So we have the principal quantum number, the angular quantum number, and the magnetic quantum number, and we have the principal being n, which is how much energy, what energy level that electron is, the angular quantum number, which is the shape, and the magnetic quantum number, which is the orientation in space. So, we have our three-dimensional axis in space, and they're oriented along those three dimensions. And that's what m sub L does. N is the largest number you can have. So if we had 3, L is n minus 1, so you could have 2, 1, and 0, right? And then magnetic is based on minus or positive L, so 3, 2, 1, 0, 1, 2, 3. Would that be for 4? N equals 4. But okay, so those are our numbers. Let's look at them again. The distribution, really we only solved this back in my day up until the advent of the supercomputers that are linked together. We could only solve the one-body problem. Now they have a two-body problem, but this is just for helium, right? And then we adapt it to all the other elements. So we model the other ones based on what we observe with the element with one electron. So basically we try to look at it as like an apple dropping apples from a tree. The average apple drops how far from the tree, and it depends on the shape of the tree and how far the branches extend, etc. But we don't really need to worry about that. So what about the principal relationships? N determines the energy of the electron. It determines how far from the nucleus the electron is, right? So the bigger the N, the farther away from the nucleus, the higher the energy. All electrons with the same N are said to be in the same principal shell. L is the shape of the quantum number. Allowed values are 0, 1, 2, 3, up to N minus 1. There are no negative shapes. There are only positive shapes, right? So if you have N equals 4, you can have a value of L, or you can describe the shape of S at 0, P at 1, D at 2, and 3 at F, right? And as that increases, the orientations also increase. So electrons with the same L are said to be in the same subshell. Now you'll hear people throw shell and subshell around in all kinds of different ways and make huge distinctions, but generally once you get familiar with the shapes, you know that the shapes are subshells. So L equals 0 is an s orbital. S orbital is a sphere, so every level of n you go to where L is 0, it's just a bigger sphere. L equals 1 is a p orbital, so the same thing happens. This dumbbell shaped thing here, or like how you used to draw flowers when you were little, right? Elliptical flowers. And then, so which is a half sphere. The p orbitals just get bigger as you go down. They're always the same shape, but as that n number increases, that dumbbell gets bigger and bigger, and there's a larger variety to find it. So if this p is right here, if you, by the time you get to the large one, the p orbital is like this, and so there's a huge distribution of those electrons there, which are farther away from the nucleus. And then L equals 2 is a d orbital, and so that could have an orientation of 2, 1, 0, 1, minus 2. M sub L is the orientation of the quantum number. Allowed values of M sub L are 0, plus or minus 1, plus or minus 2, plus or minus 3. How many ways can a sphere orient in space? One way, right? Because no matter how you look at the sphere, it's always a sphere. Try to sneak up on it, get over here, it's still a sphere, still one location. Even if you rotate it this way, it's always the same, it's still a sphere. So if you look at a P, it can be oriented 3 different ways. It can be straight up and down, which would be this one. It can be across the y-axis, or it can be across the x-axis. So x-axis, y-axis, or z-axis. So 3 orientations for P. And you can see if you put them all together, it's kind of like it's missing half the sphere. For L equals 2, there are 5 orientations. It's a little more complex. You get in dxy, dxz, dyz, dx squared minus y squared, and the dz squared orbital. Higher L labels, like 4 equals G, 5 equals H, we haven't found those electrons yet. We haven't found those elements. We haven't made them. They're probably out there in another dimension. Maybe they're what composes the other 95% of the universe that we don't know anything about. No one knows. So how do orbitals change with N? N controls orbital size, controls the number of radial nodes. We're not going to talk about that, I already said that. So let's not talk about the radial probabilities. Let's look at what happens with electrons. The total number of electrons increases as you go down the periodic table and as you go across. So N equals 1, the only orientation is the sphere, right? And it can only be oriented one way, and so it can have one type of electron, one shell. Each shell has 2 electrons though. And then when you get to N equals 2, right, then you can have the S orientation and the P orientation. It can be oriented, the sphere can only be oriented one way, so there's one orbital, but the P can be oriented 3 different ways, as we said, so there's 3 different orbitals, each with 2 electrons, so 6, 8 electrons. And so when you fill the S orbital with 2 electrons, it's stable and happy. When you fill the S and P with 8 electrons, it's stable and happy. When you get over here to the 0, 1, 2, and you fill the D orbital with 5 stable electrons, that's 18 electrons. It's also stable. That's the way we explain it. There are exceptions, and today it's coming under attack, often by advanced chemists, theoretical chemists who don't like the 18 electron rule being stable, but it's a great way of explaining why things stay the way they are. It's still a good theory, and obviously you can get into greater detail when you know more about it. But all we need to know is S is 2 electrons, P is 6 electrons, and D is 10 electrons, and F is 14. And we can fill all the elements on the periodic table with those numbers. So for an electron in a specific orbital with quantum numbers N, L, and M, the designation is NLM, where L is the letter designation, M sub L is the axis label. Examples 3S, 4PZ, 3DXY, 2DZY. We're not going to be labeling our axes. We don't need to do that for this class. What orbital type has N equals 5, L equals 2? Well, L equals 2, we already know that's a D orbital, right? So, and M sub L is minus 2. So we don't really know, and you can say M sub L doesn't directly relate to X, Y, Z because it could be any of those 5 orientations. We don't know which one it is. All right, 3DXY, that we do know. Draw it because that's given, right? That's a plane. But when you just have a minus 2, you don't know what the orientation is. But if you give the M sub L, then you know the orientation. But I would never ask you to draw dx squared minus y squared. Although, you know, back in my day, people had to do that, but now we already know. We can just look that up, or we can do other things. Draw an electron orbital with an N equals 4, L equals 1. Well, L equals 1 is a p orbital, right? And an XY nodal plane. So that would be, drawing radial nodes is a bit tricky, so it wouldn't really make you do that. You just orient it on the XY. That's all. Okay. So we did this before, but all we have to do is which is allowed, which isn't. Well, if you have an N equals 4, L can be anything up to N minus 1. So 2 is definitely up to N minus 1. So that's good. And then M sub L is 0. Yeah, because M sub L can be L from 2 to minus 2. So that works. Then N equals 3, L equals 0. Well, that seems good. Oh, but a sphere can't be oriented at the minus 1 position. So then N equals 2, L equals 3. Well, L equals 3 is not N minus 1. Right? So it's too big. You can't have a P, you can't have a D orbital when you only have an S and a P orbital available, right? So we don't even have to worry about the plus 2. So N equals 5, L equals 2, well that's good. And that's, so what? That's a D orbital. But N equals minus, M sub L equals minus 3, that's bigger than L, can't do it. Okay. And then N equals 3, yay. L equals 3, no. Because that's not N minus 1. And L has to be less than N. So, not allowed. There's one additional property, right? And that is the spin orientation. So they ran some Ag atoms through a slit, and a magnet, right? So you just shot them through there. And when you do that, they go into a plus and a minus orientation. So all the electrons aren't the same. They also have orientation. And we call it up and down or plus or minus spin. So that's the fourth orientation, is their magnetism. And we define the magnetism by saying they spin in one direction and the other one spins in the other direction. So clockwise spin, anti-clockwise spin. But it's just a magnet. We use spin to determine magnetic, but it's really a quantum number, not a physical spin, right? So you have off and on. One's off, one's on. Okay, so we're gonna have N, L, M sub L, and the spin, plus or minus. And that, we went through this table again. This is just a table that orients it, so make sure you know, you can pick that up by how we look at the electrons. So now we're gonna actually put this to use, right, in our orbitals and our periodic table when we're describing any element. So electron configuration, electrons are in the L sub equals 0, which is the sphere, right? And then electrons occupy the N equals 1 shell. So the very first one, S2, 2 electrons in this orbital, that would be what? Hydrogen, helium, because helium has 2 electrons. Here's another example. 1, so this is the orbital, the N number, right? This S is the L orientation. 2 electrons, so filled S shell. Then the next level here, I mean, this is wrong, right? Because we're leaving out, you can't have a 2p without having a 2s, right? So we need to fix that. And the same here. I don't know where need to fix that. That is just not good. So let's do this. Yeah, it's not gonna work. Yo. Come on. Gotta be smarter than this life. And in this day and age, that's not gonna happen. Really? And then next year I'll look at it and I'll have to do it all over again. So you can't go from a 1s2 to a 2p6. You have to go 1s2, 2s2, 2p6 because you have to fill the orbitals as they come up. All right. And so this one, 1s2, 2s2, that's 4 electrons. So this is the number of electrons. The superscript is the number of electrons. So this one has 2, 4, 10, 12 electrons. So whatever has 12 electrons, which is whatever's next to sodium. Okay. It's like quantum numbers give us the address to deliver, blah, blah, blah. Okay, Pauli exclusion principle. That means none of us get to go to Cal Poly, which is my old joke. I say it every time, so Patty, I'm sorry. No 2 electrons can occupy. What the? No 2 electrons can have the same quantum numbers or can occupy an orbital within the same 4 quantum numbers. Or only 2 electrons at most can occupy each specific orbital. That's our plus and minus spin. These paired electrons must have opposite spins. So that's what Pauli says. You can't have electrons with the same 4 quantum numbers, which means you can only have 2 electrons per what? Orbital. So write a configuration with 2 E's in 1s, 2 E's in 2s, 3 E's in 2p, and no E's in 3s. So how do we indicate which orbitals, m sub l, and which spins, m sub s, the electrons are in, right? Well, it turns out that we have degenerate orbitals. That would be, we call them degenerates. I don't know why, they're all the same energy, but it's not. They're all the same energy, so we call them degenerate orbitals. So it takes energy to pair an electron, right? So if I have 1 electron here, I can put another electron at the same energy level, cheaper than I can put one at the other orientation and pair them up. Why? Because they're electrons, and if you put them close together, they're going to want to push apart. So it takes energy to pair them up. It doesn't take energy to put them in the same level. So we fill up each level first before we pair them up. And the orientation of this one is wrong, but that's okay. Right. So each box, these are what we call orbital diagrams. They describe the state of electrons. And why would that become important? Well, it becomes important to know where the energy is so that we can tell which electrons are being affected. So if your energy stopped right here, you would say, oh, look, there's 2 spaces to pair up, 2 places to bond, 2 places to either take electrons or put electrons in, right? Here, if it stopped here, you could say, oh, I can take those 2 electrons off and maybe do something with this compound. Here, same thing, right? It's gonna be a lot easier if I'm out here in the 3p. Why? Because it's farther away from the nucleus, so the electrons are held more loosely. So we can have 3 spaces to bond, or we can remove 3 electrons, whatever we want to do, right? It takes more energy sometimes to remove them than it does to put them on. And when we're talking about the Born-Haber cycle in lab last time, right? We have electron affinity, which is the ability for something like chlorine to pull an electron. And we also have ionization energy, which is to remove an electron. So ionization energy is how much energy it takes to remove an electron from an atom. Electron affinity is how great can I pull an electron in? How much energy can I get by doing that? Or how much energy does it take? So how many ways can we specify 1s2, 2s2, 2p2? Well, which arrangement is best? So we can pair them up in the top box, right here. Where's my pointer? Okay. Oh, I'm not in the slideshow, that's why. We gotta obey Pauli, right? So we're either gonna pair them up or non-pair them up. And we can't put more than 2 in there. So if we were in the p orbital here and we paired them up, that would cost us energy. So we wouldn't do that. Or if we put them here, they'd be paired up, we wouldn't do that. Here they'd be paired up, wouldn't do that. But we could put them like this, or like this, or like that, and do any of them matter? The answer is no. So any of these 3 are acceptable, and we call that Hund's rule. For degenerate orbitals, the lowest energy configuration has the most electrons with the same spin. Maximize the number of unpaired electrons. So we put an electron in before we pair it in the degenerate orbitals. Well, does S have degenerate orbitals? No, because there's only the sphere. So you would always pair up the S orbital. You go to P though, now you have 3 choices, so you have to put in 3 electrons before you pair them up. And that's just explaining what we've observed. If you get to the D orbital, which are the transition metals, the block in the middle, now you have 5 orbitals that you have to fill before you start pairing up. And there's an energy cost to pairing them up. Now sometimes, like in the D and the Fs, when you get to the end there, it is cheaper to pair them up than it is sometimes to leave a half-filled shell. All right. So here we go. These are our favorites. Those are the same ones that we just looked at. Not those, but any of these are the same, right? Because these are all same energy levels. So it really doesn't matter if it's px, py, pz. It's still, they're all the same energy level, so you can put them in any orbital. And they're just as likely to be in one as the other. Because remember, we're just looking at the probability of where the electron is. So what do we know so far? Hydrogen atom has 1 electron and is greater than 1 electron. All other atoms have more than 1 electron, I should say. 1 electronic configuration, ground state. Right? It's because you can excite a hydrogen electron, remember? You put energy in, it makes it quantum shift to like the n equals 5, and then drop back down to n equals 2, which we can see. But if it drops back from 5 to 1, we can't see that transition, right? We can only see the 5 to 2, 5 to 4, 5 to 3 transitions. So our detectors are, as human beings, miss a lot of things that we can catch with other types of detectors that are more sensitive or have a greater range, which is why it's hard for us to understand all the things going on around us. No Pauli exclusion principle or Hund's rule needed, right? Because we only have 1 electron with hydrogen. All other atoms, Pauli exclusion principle and Hund's rule apply, which is Pauli exclusion principle, you can't have more than 2 electrons in the same shell because they all have to have different quantum numbers. Hund's rule says you can't pair them up until you have all the equal energy degenerate orbitals full. Orbital energy only depends on principal shell. Question mark on the other atoms, we don't know. There's other stuff, right? Once you start, you have more charge in the center and more charge on the outside. Now there's different effects going on with that element, right? Can the nucleus see each shell? Are there electrons in the way, or is there what we call shielding? So we'll talk about that. So the exact solution you can do for helium, lithium, you have a solution for the wave function, the Schrodinger equation. The multi-body problem, not so much, right? Too many factors occurring. But as our models get better, as our computers get better, we may be able to solve these. And then, I mean, that's really part of what's going on. Chemistry really, you could go to way back and say, why were there chemists? Because there were people who wanted to turn dirt into gold, right? The closer we get to solving these problems, the more we understand how each element is different than the other, leads us to try to get closer and closer to transmuting elements into what we want, right? And that's what nuclear power is. It's a transmutation of uranium and taking advantage of a naturally occurring radioactive process and then enhancing that process so that we can control how much comes off. And if we can do it the other way, so in radioactive power, we take radioactive decay and we use that decay as energy. But what we want to be able to do is take the radioactive decay and make it go the other way. Fuse elements. And there was supposedly a big breakthrough. I haven't read the article yet, so I'm not really familiar with it. But there's been a big jump in fission, which happens about every 10 years. Somebody says, oh, we've got fission now. We can do it on our desktop or our laptop. And, not so far. But that would solve our energy problem, for sure. All right. Orbital energies, shapes, and NLM relationships for all elements are similar. So it's our model, right? What we're looking at is the model. We're not really saying what an electron shape is. We're saying for this element, the probability is very high that we can say with a little bit of certainty where the electrons are around the nucleus, which is not, written in stone. Okay, so the effective nuclear charge Z, I'm probably not going to ask you about this, but it's good to know. Normally I would. Higher nuclear charge, but we missed 2 weeks. Lowers orbital, because of me. Higher nuclear charge lowers orbital energy by increasing the nucleus electron attractions. The effective electron repulsions, so shielding. So we have an effective nuclear charge in the center, right? You stabilize anytime you want something to be more stable, you lower the energy, right? You want to be more stable, tone it down a notch. You want to be highly reactive, just keep up in that energy. Okay. So, effective electron repulsions. Electrons, same charges repel. Unlike solvents, where like dissolves like dissolves like is for solvents and does not mean the same thing when we're going to electrons or protons. They repel each other. So additional electrons, as you add electrons to the outside of the element, now you're going to have electron-electron repulsions. Additional electrons in inner orbitals shield the outer electrons more effectively. So the electrons around the interior orbitals, the electrons that are closer to the nucleus, lower the energy levels of the outside orbitals because the nucleus can't see them as well. Okay, we're just going to go through that. Basically, the outer electron is shielded from the full nuclear charge. So as you put more protons in the center, there's more charge, but to keep the orbitals at lower energy, they're shielded because of the electrons on the outside. So you have this high density charge in the center, separated by neutrons that allow the protons to be close together. And then you can add electrons because the electron repulsions can be overcome because the nuclear charge in the center shields those electrons. The nuclear charge that electron sees is not Z, but a smaller amount Z effective, or the effective nuclear charge. So what does that mean? Lower end orbitals shield higher end orbitals. So basically, that's how we say we can hold the molecule together. That's all we're talking about. The farther away you get from the nucleus, the more the inner electrons shield the outer electrons. L energy levels are not degenerate in energy. Oops. So I just got done saying they are, but they're not, because why? The farther away, the orientation makes a difference, because the orientation tells you how you can see the center. So NS is less than NP, which is less than ND, which is less than NF. All right. Okay. So what does that mean in terms of how we fill out an orbital diagram? So in simple, in numbers, 1s is the lowest, then 2s, there's nothing to interfere there, then 2p, so it's just our straight progression, 3s, 3p. But then, because of this shielding effect, the 4s is lower in energy than the 3d. So when we go to fill, we fill 1s, 2s, 2p, 3s, 3p, then we go back and fill the 4s, and then we fill the 3d, which is why the transition metals are lower in energy, one rung down, because we have the 4s filling before the 3d. Okay. Now within the subshell, the px, the py, and the pz are the same. However, this guy's out of whack, right? The N4s is lower than the 3d, and then when you go to the 5s, same thing happens. And here's another breakdown of it. And this is the capacity, right? So here's the 1s with 2 electrons, 2s, 2 electrons, 2p, 6 more, 3s, 2, 3p, 6 more, 4s, 2. Which is why there's nothing, on your periodic table, there's nothing between those levels of electrons, right? But then when we get to the 4s, right, now all of a sudden we go 4s, and then we have to fill the 10 electrons of the d orbital. Then we fill the 4p. So that's why there's the transition series in the 4th row, because we're filling the 3d orbital, which fills after the 4s. And then the same thing happens. We go to the 4p, then we go to the 5s, and then we fill the 4d, we drop back down. So that transition center with the d orbitals is filled after the s orbitals. And then 4f comes in after 6s. 4f, then 5d, then 6p. So there's another drop when we get to the lanthanides and actinides. We drop down again. So that's why they're lower on the table, or the way we used to show it. Sometimes now they expand the table, but right, have 2 sets of transitions. All right. So here we go, more expanded view to show you again. L equals 0 is just the S progression. L equals 1 is the P progression. L equals 2 is the D, and L equals 3 is the F. Right. And you have to get all the way to the 6S to get to the 4F. And again, we're always increasing energy as we change that end number. And so this is the actual list, right? 1S, 2S, 2P, 3S, 3P, 4S, 3D. I'm not going to make you memorize that, but there are people who would. Maybe. No one. I don't even think anyone here would do that at this point. So. We also have a way of creating a shorthand for filling out elements, right? And that is to use the, let's look right now. So if we want to take charge of lithium, we're going to give 3 electrons. We fill the 1s orbital first with the first 2, and then we add 1 to the 2s. Then we're going to do beryllium 1, 2, 1, 2. Why? Because there's no degenerate orbitals. You just fill them as you see them. And then we get the boron, you do 1, 2, 1, 2. We fill the 1s, the 2s, and now the 2p. We get to carbon, fill the 1s, the 2s, and then we have 2 lone electrons. So why does carbon want 4? Because 1, 2, 3, 4, and now it has a happy p orbital. Okay. and then it could also lose 4, right? And now it has nothing in there. And why do we want to do that? Because we want to get to an island of stability. We call the p orbital, the 8 electrons in a shell, in the S and P, we usually call that an island of stability. What has that are the Nobel gases. All right, so this is the way we fill those. And you can see right here, right, the shorthand is to compare it to a noble gas. So you can write the noble gas configuration for the element right before that. So in this case, the helium's the noble gas, and it's going to be helium plus 1 electron. Down here, when we get to sodium, number 10 is neon plus 1 electron. And so that's how we do it. There's the neon right there, 10. So we can write a shorthand using the Nobel gas that comes before, because why is that the case? Because we can always, right, all the electrons that come before the next electron are in the element prior to that. So nitrogen has all the electrons that carbon does plus 1. Neon has all the electrons that nitrogen has plus 1, but when we get to the noble gas configuration, we just use that as a shorthand to save time for the next element. All right, so do we want to look at this? No, same thing. Right, but here's a, I guess we do. So neon with 1 electron, then magnesium is, you use the brackets around the symbol for the element, and then add the electrons that are in the next space. So very easy, another easy way of notating what the difference between elements are, which electrons are going to be used. So obviously, this is showing the valence electrons for each element. All right, so we have 2 types of electrons. We have the inner core electrons, all the electrons in completed principal shells, the previous noble gas, right? We also have to say the core is not involved in chemistry. Core electrons stay with the element. They're not going to be, because why? Because the chemistry happens on the outside, not on the inside, which is the exact opposite of psychology. Outer electrons, all the electrons in the highest principal shell. So the N number defines the outer electrons as well as the inner electrons. Valence electrons are the outer electrons used in forming compounds, whether we transfer electrons in a redox or whether we have ionic bonds or we share electrons covalently, it's always in the outer shell. So if a big element with N equals 5 gets together with an element of N equals 1, it's still taking place on the outer edges of both elements. There's one more principle, the Aufbau principle. The electronic configurations of every element can be obtained by adding electrons to the lowest energy orbital available. So fill lowest first is what that basically means. And there's some exceptions, right? To the N number rule, we already talked about that. The 4s fills before the 3d, and the periodic table shows you that. So if you can't remember, you can just look at the periodic table. And a lot of people write 3d above the first transition metal so that they know that you step down 1. And then there's another trick this way with the arrows, but again, you're not going to have to remember that. And I don't even think on this test I'm going to have you do an orbital diagram. I don't think. And so here's what I'm talking about in terms of the group. So here's the 1s, right, with 1 electron for hydrogen and 2 electrons for helium, and then the 2s, the 2p, the 3s, the 3p, 1, 2, 3. So phosphorus has 3 unpaired electrons in the p orbitals, and then 4, 5, 6. Now they're paired up again, and then we go to the 4s, and then we drop down to the 3d. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so zinc has all its electrons paired. And why is that? Why is zinc 2+? because instead of dropping the 3d electrons, it drops the two 4s electrons. So it acts and behaves like a 2 plus most of the time. You can force zinc to do other things, but it's very difficult. It takes a lot of energy. Right, and then if we drop down, here's the 4F down here, and then the 5F. And let's go. S block, P block. This is a good way to differentiate where the electrons are in the blocks, right? And this is going to be the D block and the F block. So like a prison, you have your elements are not allowed to mingle outside their block. Right, and again, in the fourth row, or n equals 4, when we get to the D block, we drop one level. And all the way across, right? And then the lanthanide, same thing. Right. Okay. Configuration within groups, the reason that all the alkaline metals are 1 and 2 is because they have the same electronic configuration, so they behave the same way within a group or family. Similar outer electron configurations correlate with similar chemical behavior. Again, you act like your family. Who knew? My family would say that's not true. I know them. Navigation to get configuration of lighter elements is easy. For selenium, this is usually the one I have you do, but noble gas core. So that's what I'm talking about. If you wanted to find selenium and you don't want to add all the way, do all the electrons to 3p, 8, 6, then you would do the noble gas argon plus 4s2, 3d10, 4p4, and that would be the shorthand for selenium. And what is the number of unpaired electrons? Well, if you're in the 4p, 1, 2, 3, now you got to pair up one of them, so 2 unpaired electrons. And if you have unpaired electrons, it's called, your element is paramagnetic, and if it is, it's not paramagnetic, it's diamagnetic, which means all the electrons are paired. Okay, groups, periods, rows, yes. Exceptions to off-bout. Oh, I hate this part. But we're not testing on it, so it's okay. NS and N-1D energies are very close. Half and full-filled N-1D shells are extra stable. So 4s1, 3d5, not 4s2, 3d4, right? There's a stability of filling the degenerate orbitals over pairing up. Makes sense, right? Why would you pair up if you can stay at even energy? And so you don't. You gain energy by not pairing up. And then once that's full, now you jump back. 4s1, 3d5, not 4s2, 3d4, and 4s1, 3d10, not 4s2, 3d9. Okay. 5d and 4f energies are even closer together. Half full and full filled shells are extra stable. So 4s2, 4f7, 5d1, not 6s2, 4f8. So there's like 4 exceptions, right? Well, 8 exceptions. But we're not even gonna look at those right now. So 6f, many exceptions are known. So as you get farther down and things get closer in energy, the traditional rules don't apply as much. Pay most attention to exception 1. That's usually my way of saying, I'm gonna put that particular element on the test, but we're not testing on this, so. Yeah, more orbital configurations, not into it. Right, the paired and unpaired, remember, if it's the same energy level, it doesn't pair up because why? Because it costs energy. Everything we look at is about energy. Is it does it cost us energy, or do we gain energy from doing it? And that's why the battery conundrum right now is so hard for me to wrap my head around, because it's not sustainable, right? You have to create energy to make the battery. You have to use energy to make the battery. You can only charge the battery so many times. When we were taking gasoline and burning it, creating carbon dioxide and water with some impurities, we can always recycle carbon dioxide and water. But what do we do with the lithium? What do we do with all the battery components? I don't know, but that's for you guys to figure out, because we're headed that direction rapidly. Okay, so that's that, and that's enough of that. So let's call it an early day. We'll take 10 minutes in the meeting lab, and which is also going to be an early day, or maybe not. I mean, it depends.